Before we introduce the main topic of this section, the mean value theorem, let's start with the special case, Rolle's theorem. And so even before we get rolling, here's another Venn diagram. Like Rolle's is a special case of MVT, and even though we don't know what either one of them is yet, there's always this back and forth of, should we teach the big picture one first and then talk about the special case, or should we talk about the special case because it's easier and then try to expand to the bigger picture? Well, this year we're going to start with the special case and then talk about the overall case. Rolle's theorem activity. So we'll kind of walk through this together. Place 2 points, read this one carefully, place 2 points anywhere on the coordinate plane below that have the same y values. And you probably want to spread them out. So like don't put 2 points like right next to each other. So whatever y value you like, I'm going with 3. So I got 2 points. Now everyone's going to copy my points, which is fine. Connect the 2 points with a continuous function that is also differentiable. So continuous, no jumps, no asymptotes, no holes. Function meaning vertical line test, right? So you can't double back on itself and not have it not be a function. Differentiable, so no cusps. So I'm going to let you connect your own 2 dots with a continuous differentiable function. So play connect the dots. Don't wait for me to do mine. You do yours. However you want it to look. I mean anything, but it's got to follow the rules. So you can't go too crazy. Would that qualify? Why not? It's not a function. Would that qualify? Why does that not qualify? There's a cusp. How about that? It's not continuous. So connect them however you want, but there's definitely some things you're not allowed to do. So hopefully you did something other than like a straight line, although a straight line would still work. Conclusion. We're already on a conclusion here. There must be at least one point on your function where you can draw a tangent line that is horizontal. So there should be at least one spot where you can draw a horizontal tangent line. I happen to have 2. If you got crazy, you might have 3, 4, or 5. This activity models an important concept called Rolle's theorem. So here's Rolle's theorem, the fancy way to say it. Let f be a function that is continuous on the closed interval a to b, differentiable on the open interval a to b. If f of a equals f of b, then there is at least one number in c, or one number c in a to b, such that the derivative is 0. Boy, that's a lot of words. But your picture is the important thing. If you start with, let me try to condense Rolle's into simply as we can. If it's continuous on the closed, if it's differentiable on the open, By the way, those are always going to go together. Continuous on the closed, differentiable on the open. There's going to be more theorems we learn, but it's always going to be continuous on the closed, differentiable on the open. And then lastly, if f of a equals f of b. So if the two y values are the same. So if you meet those three criteria, then somewhere the derivative is 0. F prime of c equals 0. What most of the homework questions are gonna look like, are gonna say, is does Rolle's apply? So you have to go through your checklist. Is it continuous? Is it differentiable? Is it does f of a equals f of b? The endpoints, do they have the same y value? And then if so, find c. That's almost always how Rolle's problems are set up. Like, does Rolle's apply? And if it does, figure out where the derivative is 0. In fact, right off the bat, determine if Rolle's theorem applies to f of x equals this function between -2 and 2. State thoroughly the reasons why or why not the theorem applies. This is a part where we might start missing points on tests because you jump to the end without stating and showing that Rolle's theorem works. So for Rolle's to work, it's got to be continuous, differentiable, and the y values have to equal each other. So f of x equals x to the 4th minus 2x squared. All right, I don't know what that looks like, but I think I can make conclusions about continuity and differentiability. Do you think this thing is continuous? And if so, why? And if not, why not?
Yes.
Why is it continuous? It's a polynomial. And that's the same reason it's differentiable. Because polynomials are continuous and they all have derivatives. They're all nice and smooth. They don't jump around or do anything crazy. So we have to say that f of x is continuous and differentiable. And we can say because it's a polynomial. So there's our first two bullet points of the if part. It's continuous, it's differentiable. Now we need to check the y values of the endpoints. So we need to find f of -2 and f of 2. And what are we looking for when we do this? What are we hoping to find? Before we find c, though, when I look at f of -2 and f of 2, I want them to be equal. If they're not equal, then this problem is done. So maybe I don't want them to be equal, but if they're equal, I can keep going on the problem. So f of -2. So now I need to state that they are equal. Right, I'm looking at my if, continuous and differentiable, got that. And then lastly, I need to say f of -2 equals f of 2. First statement was determine if it applies. So I need to state that it applies. The little triangle made out of 3 dots. I don't know if y'all have seen that before. That means therefore in math language. Therefore, Rolle's applies. But that's going to be half the points on a test, is getting that much. You can't just jump to the then and figure out where the derivative is 0. I mean, that is where we're going next, but that's only half the problem. The first half is getting through the if part of the problem. So that's the if part. The then part says that f prime of c equals 0. So let's take a derivative. 4x cubed minus 4x equals 0. So I can factor out a 4x. That leaves x squared minus 1. So x equals 0, x equals 1, and x equals negative 1. I do need to be careful to make sure all of those are in the interval we started with. Because sometimes it's cruel, but sometimes you end up with an answer that's outside of the interval, so you'd have to throw it out. But all of these are on negative 2, 2. So we're good with those as our answer. Confirm your result by graphing the function in the coordinate plane to the right. Well, you can trust me. This is what the graph looks like. Something like that. And so, sure enough, there are 3 places that have a horizontal tangent line. Again, to kind of emphasize, the first part is the if, the second part is the then. Don't jump just to the then part. You got to show the if part so that the then part makes sense. All right, well, that's kind of it for Rolle's theorem. So continuous, differentiable, y values are the same. Then those 3 things, if that's true, then somewhere the derivative is 0. Now for the mean value theorem. This is more, it's along the same lines, but it's more general than Rolle's. Rolle's is a special case of MVT. All right, mean value theorem. If f is continuous on the closed interval, differentiable on the open interval, then, so let's actually back up a little bit and let's do the super condensed version out to the side here. If continuous on the closed, differentiable on the open, then is that equation right there. So compared to Rolle's, what are we missing from the if part? What's different? Endpoints don't have to be the same. So Rolle's is a special case, meaning the y values of the endpoints are the same. For mean value theorem, they don't have to be the same. They can be different. Let's see if we can figure out what this means. F prime at c. So that would be the derivative of f at c equals f of b minus f of a over b minus a. Well, let's start with the left-hand side. So f prime of c, that's like calculus slope. Or instantaneous rate of change at c. is f prime of c, the derivative at c. What's the right-hand side? Do you recognize what that is? You've seen it before, so you recognize it. You remember what we call that or where you've seen it before? Tried to give you some hints because it's not the calculus slope, it's not the instantaneous rate of change, but it's
one of the different definitions of
it's not that. Somebody said, I think, the average what? That's the average rate of change. What else is it called from your Algebra 1 days? That's just slope. Or algebra slope, maybe. Yes, you got so deep into calculus you forgot and you didn't recognize good old algebra slope. So, yeah, f of b is a y value. So this is y2 minus y1 over x2 minus x1. So MVT means that the calculus slope somewhere at C equals the algebra slope. And the algebra slope is the overall slope. So from A to B is the algebra slope. Somewhere that equals the calculus slope. Let's see if we can make sense of this. Visualizing the MVT. Well, it's not even have to be a straight line. It can be any line.
No, but like you have like the curvy line, and then while you had the curvy line, you drew a straight line.
Yes, yeah, that's exactly what we're about to do. Your question is exactly what we're about to do. Let's do it. In the figure to the right, label the indicated ordered pairs. So this ordered pair, and let's label them with this notation. So the x value is a, the y value would be f of a. X value is b, y value is f of b. Label a segment whose length is f of b minus f of a. Okay, this gets a little bit strange how they walk us through this. Label a segment whose length is f of b minus f of a. So that's the change in y. So that segment is f of b minus f of a. Label a segment whose length is b minus a. I think you see where they're going with this. This is like way back Algebra 1 type slope. Change in y over change in x, rise over run, y2 minus y1 over x2 minus x1. That's all going on right here. The quotient, f of b minus f of a over b minus a, is the blank of the segment joining the 2 points. Well, the 2 points are the a comma f of a, b comma f of b. So what, you know what word goes in this blank? The slope. And I'm going to put slope and then in parentheses algebra, because sometimes we talk about calculus slope, sometimes we talk about algebra slope. That's definitely the algebra slope. Draw in this segment. Andrew, that's exactly what you wanted to do. So if I draw in that segment, and I even drew it in with a popsicle stick already labeled. Like, you don't have this popsicle stick, that's okay, but that's my algebra slope, f of b minus f of a over b minus a. Number 5. f prime of c gives the blank of the line. Okay, I don't know that you would know what words to put in here. Blank of the line, blank to the curve. Any idea what goes in those two spots? I mean, they're words you've heard of before. What does f prime tell us? Okay. I would yes. And what's another word for derivative? Instantaneous rate of change. So I'm going to say, those are both correct, but I'm going to say slope, parentheses, calculus, which is the derivative, which is the instantaneous rate of change. So those are all correct answers. Of the line, blank to the curve, tangent to the curve, at the point C, comma, f of c. On the graph above, locate the c value that is guaranteed by the mean value theorem and draw a line tangent to the curve at x equals c. So somewhere on this graph there is a tangent line. I got my popsicle stick serving as my tangent line. But somewhere along there, this popsicle stick tangent line has the same slope as the algebra tangent line. The average rate of change. Somewhere the instantaneous rate of change equals the average rate of change. So I'd say about right there. So about right there is my c value, whose derivative is the same as the algebra slope. Locate c, did that. Draw a line tangent to the curve at c, did that. Here's another way to visualize it. So the purple one was the algebra slope, the algebra rate of change. The average rate of change. The other one was the calculus slope, the f prime at c, the instantaneous rate of change. Those two lines, this is number 7, the two lines drawn on the graph, my two popsicle sticks, are blank to each other. Parallel. Here's MVT in a super condensed form. If it's continuous on the closed, differentiable on the open, then I'm going to just write it again. The calculus slope is equal to the algebra slope. Although calculus slope at x equals c equals the algebra slope. The algebra slope doesn't have a specific point because it's the algebra slope. You can't have an algebra slope at one point. You got to have this overall algebra slope is equal to the calculus slope somewhere. And your job usually is to find the somewhere, just like it was in Rolle's. Like find c, that's usually the MVT problem, is find c. Thus, the conclusion of the MVT can be restated. That's what we just did. I think my way is better than this way, but it's another way to say it. There will be two parallel lines, one through the points A, f of A, B, f of B, and the other tangent to the curve at C, f of C. But to me, the easiest way to remember MVT is that the calculus slope equals the algebra slope. The IROC equals the AROC. Instantaneous rate of change equals the average rate of change. The key is at C. I can't even read that, but calculus slope is at a specific point. Instantaneous rate of change is at a specific point. MVT problems are kind of like Rolle's problems. Does it work? Meaning, do you meet the if? And if it does, find C. Number 2, illustrating the mean value theorem. And by the way, mean value theorem is so common that it's frequently abbreviated MVT, and that's okay. If you use that abbreviation on the AP test, they'll know exactly what you're talking about. Determine if the MVT applies to this function on the interval 1 to 5. And they were nice enough to graph it for us. State thoroughly the reasons why it does or doesn't work. So that's the if part. If the theorem applies, find the value of C. All right, well, the if part is continuous on the closed, differentiable on the open. So this one's nice because they give you the picture, so you can know it by the graph. So is this thing continuous and differentiable between 1 and 5? Yeah, it's fine. So you can just say yes, see the picture. You didn't have to do anything on that one. Where would this function not be continuous? Where would this function not be continuous? At 0. So you could also go that way. You could say it's only discontinuous at x equals 0. So you can't just say, oh, the function's continuous. You'd have to say it's continuous between 1 and 5. If our interval included 0, we'd have to throw it out and say MVT doesn't apply. We're done with this problem. But our interval doesn't include 0, so we're good.
Is there another
Like a horizontal asymptote? Yes, there is. There is. That doesn't really matter to this problem, but yeah, there is a horizontal asymptote. Because as x gets really, really big, this function would approach 3.
There's also there's a vertical interval.
Yeah, and there's a vertical asymptote at 0, but we're not concerned about that because we're only looking from 1 to 5. All right, MVT applies. So again, here's how I think about the problems, how I work the problems. The calculus slope equals the algebra slope. That's what MVT means. So the calculus slope is the derivative at c. That's what we're looking for, c. The algebra slope is good old y2 minus y1 over x2 minus x1. So let's fill in all those pieces, and we're trying to find c. So there's a lot of pieces to solve here. I need f of b and f of a. So I need f of 1 and f of 5. So f of 1, plug in 1, 3 minus 5 is negative 2. F of 5, 5 over 5 is 1, 3 minus 1 is 2. First period, because it's a Wednesday schedule.
It's a Wednesday schedule?
Yes. So let's see, f of b is 2, f of a was negative 2, b minus a is 5 minus 1. Okay with all that? I don't want to go too fast. So 2 minus negative 2 is 4, 5 minus 1 is 4. So I've got the right hand side figured out. The slope is 1. In fact, could have done that with our with the picture if we'd really been paying attention. There's our algebra slope line. Our average rate of change line is 1. The algebra slope is 1. The calculus slope I'm going to rewrite f of x so I can take a nicer derivative, right? Because I don't want to take a derivative with the denominator. I mean, I could, but that would be quotient rule. So I'm going to rewrite it. Its derivative then would be, right, bring down the exponent as the coefficient, decrease the exponent by 1, right? Power rule. So the derivative is 5 over x squared. We okay with that? Power rule derivative. And then we want to know it at c. Well, that just means plug in c. So 5 over c squared. So our instantaneous rate of change is 5 over c squared. Our algebra rate of change is 1. Now we're just solving for c. This is now an algebra problem. So c is plus or minus the square root of 5. Yes or no on that as an answer? Well, it's no. Do you know why it's, or not quite is maybe a better answer? It's one of those isn't on the interval. So not negative square root of 5. Only square root of 5 is on the interval. Let's see, square root of 5 would be like 2.2 something. Or we could get it, we could kind of check it visually. Locate the spot where the calculus slope equals the algebra slope. And where that is the square root of 5. mean value theorem. Calculus slope equals algebra slope. Average rate of change equals instantaneous rate of change somewhere. And the somewhere is the algebra part of the problem. Number 3. Find the equation of the line tangent to the graph on the interval 0 to pi at the point which is the solution to the mean value theorem. That's a lot of words. Find the equation of the tangent line. So I need point and slope. At the solution to the mean value theorem. Okay, well, mean value theorem is calculus slope equals algebra slope. So I need f of pi, I need f of 0. That will tell me the algebra slope. And I'm going to pause for a second and let you find that algebra slope. So f of pi is kind of ugly, 2 pi plus 1. F of 0 works out nice. So 2 pi plus 1 minus 1 all over pi minus 0. So that would be 2 pi over pi, which is just 2. So that worked out okay. So I know the slope is going to be 2. Halfway done with the problem. Now I need to figure out where that is. So where is the instantaneous rate of change equal to the algebra rate of change? Well, I need to take the derivative of f. Let's see, so derivative of 2x is 2. Derivative of sine is cosine. Derivative of 1 is 0. So 2 plus cosine c equals 2. So cosine of c equals 0. Let's see, where does that happen? Pi over 2 and 3 pi over 2. Now, are we okay with both of those answers? Why are we not okay with one of those?
Because 3 pi is outside of 0.
Yeah, 3 pi over 2, we were only allowed to look from 0 to pi, so 3 pi over 2 we have to throw out. So pi over 2 is the x value of our point. How will we get the y value of our point? What's that?
Plug it in.
Just plug it in. Although, plug it in where? I got all sorts of stuff going on here. Good, into the original f of x. If I plug it into f prime, I'm going to get its derivative, which should be 0, because that's what we just found. And so I need to find f of pi over 2. So 2 times pi over 2 plus sine of pi over 2 plus 1. So that would be pi plus sine of pi over 2 would be 1. So pi plus 2. That's the y value of the point that we're concerned with. And we already know that m equals 2. The slope was 2. So that's not my final answer yet. This was a find the equation of the tangent line. Okay, so I've got everything I need. So y minus pi plus 2 equals slope 2 times x minus pi over 2. Man, what a question that was. MVT, tangent lines, trig, derivatives, algebra, a lot of stuff going on. How do I know to use 2 as the slope? Right. Well, the whole point of MVT is that the algebra slope equals the calculus slope.
Okay.
So once I found algebra slope was 2, I knew that the calculus slope was 2. Because it said use it at the point that's the solution to the MVT. So yeah, normally I couldn't do that. But because it cited MVT, calculus slope equals algebra slope, once I found slope is 2, it was what we're concerned with.
Where did you find slope?
The algebra slope is 2 when we plugged in all the algebra 1 stuff. When we did the algebra 1 part of the problem. They ended up canceling, yeah, because it was 2 pi over pi. So it was looking really ugly until everything canceled out nicely. All right, number 4, I suspect I was supposed to print at the top of the next page. When does MVT not apply? So this little section is going to go quicker because all it means is, or all we have to do is explain precisely. So I better get detailed here. Why we cannot apply the mean value theorem. Okay, well there's only 2 conditions. It has to be continuous on the closed and differentiable on the open. So that's really the only 2 things I'm thinking about. So at A, what would be the problem with A? Good. This matches the one we did earlier on the homework. Where is it not differentiable? Right. You got to give me the point. Not differentiable at x equals 3, the cusp, and 3 is on 2 to 5. So no MVT here. And that's all it wants for that one. Now, if this interval had been 4 to 7, could we use MVT? Yeah, because our cusp wouldn't be on the interval and we'd be okay. But this cusp is in that interval, so it doesn't work. Now, all of these are no's, so we just got to figure out, why is it a no? Part B. G of x equals 2 over x plus 2 from negative 3 to 1. What's going on at negative 2? So you're right, there's a problem at negative 2, but what specific is the problem? Okay, it's a vertical asymptote, it's undefined, but let's use one of these words specific to the MVT. It's not differentiable, but the reason it's not differentiable is because it's not continuous. So let's say not continuous. I guess I would accept not differentiable because that's true as well. But more precisely, it's not continuous. And again, negative 2 is on the interval we're concerned with. If we had looked at a different interval, then maybe it'd be okay. Ooh, part C. I don't see right away where like you guys were good on A and B. Like A is absolute value, so it's got a cusp. B has a denominator, so that's a potential problem. C doesn't have either one of those problems. Let's take its derivative and see what happens. So 2/3 x to the negative 1/3, which means cube root of x in the denominator. Uh-oh, I think I just realized where the problem is. So what's the issue with this one? Can't be 0, so what's going on at x equals 0? And use one of the words that go with MVT. Well, it is continuous, because I can plug in 0 here. But the derivative can't have 0 in there. So it's continuous, that's fine, but its derivative doesn't work. So it's not differentiable at x equals 0. All right, a little bit of side note on the AP exam here. On the AP exam, questions like we have seen on the previous pages are usually not asked exactly like that, but while these types of problems foster a strong understanding, typically students are asked to show that a given value for f prime must exist on a given interval. This is often done, tables or graphs, we've done that. So IVT guarantees a point. I'm not really worried about that one. MVT guarantees a derivative. MVT is just calc slope equals algebra slope. All you need to know. Not all you need to know. There's more to it. Calculus slope equals algebra slope. And again, you can use MVT as your reasoning. Today's assignment is page 174. And I will post the picture so that you can, actually work the problem. 9 through 21 odd, and 35 to 45 odd. The first set is rolls, the second set is MVT. One more quick thing. Back to that Venn diagram. So MVT is a certain set of problems. Rolls is a set of problems where the y values are equal, and that means that the slope is 0. So in some ways you don't ever have to work a rolls problem. You can work them all like MVT problems. It's just if the slope is 0, it's specifically a rolls problem. So you don't ever have to even say rolls because you can do them all as MVT. But it's a little bit of a shortcut if you recognize that the y values are the same. All right, a little bit longer lesson, but provided notes, block day, so works out okay.